Hello, welcome to S Chemistry. I am your instructor Dr. Suhas Gauri, and today I will be teaching BSc 5th semester Physical Chemistry course on nanomaterial. Here is the outline. In this class I am going to cover introduction about nanomaterial, what is meant by nanomaterial and what are the application, followed by method of synthesis of nanomaterial. In that I am going to cover high energy ball milling. So let us start with introduction. So the word nano means 10 to the power minus 9, that is 1 billionth. 1 nanometer is 1 billionth of a meter. The nanometer is abbreviated as nm, that is nanometer. Now the nanoscience and nanotechnology are the two of the latest field in today's scientific and commercial world. So these two fields are related to scientific and as well as commercial world. Nowadays, so many nanotechnology based uh, nanotechnology are coming. So this is the current topic which is in focus. So Richard Feynman is considered as a father of nano. Here you can see how where the nano word in terms of measurement it comes into the scale. So as you go down, so this is 10 to the power 1, so this is deca. 10 to the power minus 1, this is deci, it's a decimal. 10 to the power minus 2 means a centimeter, as we know 1 centimeter. So this is the unit of 1 centimeter. Now you can think about the nano, so that is the 10 to the power minus 9. So 10 to the power 3 minus 3 is milli, 10 to the power minus 6 is micro, that is denoted by mu. 10 to the power minus 9 denoted by n, that is nano. And 10 to the power minus 12 is denoted by pico, that is small p. If your length is in 10 to the power minus 15, we call it femto. And if your length is 10 to the power minus 18, we call atto. So this is the smallest of all unit in terms of any meter, second or anything. So as you go down means higher level on higher scale, so the symbol is respective and prefix are given below. So 10 to the power 1 is, we say, is deca, denoted by dA. If it's 10 to the power plus 2, then it's a hecto. If 10 to the power 3, we call it a kilo, denoted by k. If 10 to the power is plus 6, we call it mega, that is m, capital M. If it's 10 to the power plus 9, we call a giga, capital G. If it's 10 to the power plus 12, we call it tera, T. If it's 10 to the power minus plus 15, we call a penta, so P. If it's 10 to the power 18, we call exa, it's E. So like that. So now you can think about the plus and minus. So both we have seen. So this is the well-known centimeter, 1 centimeter, and pico nano is less than 1 centimeter. So you can think about how much small that unit is. So in that region we have to play the chemistry. So there are some terms involved in this chapter that I'm going to discuss now. First term is the nanomaterials. So the material, what is the definition of nanomaterial? So the matter which has dimension in between 1 nanometer to 1000 nanometer, we call it a nanomaterial. So your dimension of any material which is lie in 1 nanometer to 1000 nanometer, we call it a nanomaterial. The second term is there, that is the nanoscience. The, what is meant by nanoscience? So it is a branch of chemistry for the study of a fundamental principle of a molecule and material with dimension between 1 nanometer to 100 nanometer. So is called the nanoscience. So if your dimension is between 1 nanometer to 100 nanometer, then if whatever the material is that, if you are studying that material and principle of the molecule, we call it nanoscience. So this is the second term. What is the third term? That is the nanoscale. What is meant by nanoscale? The dimension which is expressed in nanometer or 10 to the power minus 9 meter is called the nanoscale. So it's just 1 nanometer, you can say in that way. If you can express in terms of nanometer, then we can call it, it's a nanoscale. A third term is there, that is nanotechnology, a fourth term. So what is the fourth term? Nanotechnology. So it's a branch of engineering which based an application of nanomaterial into useful nanoscale devices is called a nanotechnology. So this is a branch of engineering which based an application of nanomaterial into useful nanoscale devices. So we call it nanotechnology. I hope these four concepts are clear.
Now we will see the method of synthesis.
So various techniques and methods of synthesis are available for different type of nanomaterials. Now we are going to see what are the methods. So broadly, these methods are classified into four types, that is physical method, second is chemical method, third is biological method, and fourth is hybrid method. So any two can combine and form one method. So these four types of methods are there to synthesize any nanomaterials. So there are large number of techniques available to synthesize different types of nanomaterial in the form of colloids, cluster, powder, tubes, rods, wire, thin films, and etc. So these are the shapes of the nanomaterial. So your shape of the nanomaterial can be colloids, cluster, or in the powder form, or tubes, rod forms. So we can see now in the given figure. So this is also can classify in terms of dimensionality, 0 dimensional, 1 dimensional, 2 dimensional, and 3 dimensional. Some nanoparticles stays in 0 dimensional. That means there are these are the nanospheres or clusters, such as quantum dots, fullerene, or gold nanoparticle. So these are the 0 dimension because it comes less than 1 nanometer or 1 nanometer. So that's why we consider as a 0 dimensional. What is mean by 1 dimensional? So in 1 dimensional, there are examples are nanotubes, nanowires, and nanorods. So here, as you can see in this figure, so metal nanorods are in this kind of shape. So this can be any material, a metal or any ceramic crystal. So these are the nanorods or nanotubes. Uh, there are another example is carbon nanotube, which is made up of only carbon moiety, and it is in tube kind of shape. So that's why this is one dimensional nanomaterial. Other example is a nanowire. So that can be any length, and this length can be in terms of n number of flexible nodes will be there. So gold, that can be gold nanowire. Examples are gold nanowire, polymeric nanofibers, or self-assembled structure. So these are the nanowires. So now 2D. Now we are going to see 2D, two dimensional nanomaterials. So this is also one kind of classification in terms of dimensionality. But as given here, the material types and form of the types. So here thin films comes in 2D. So you can coat it using as a spray technique like that, carbon coated nanoparticles or graphene sheet, or can be layered nanomaterials. So these category comes in two-dimensional nanomaterials. What about three-dimensional? So in three-dimensional, generally bulk nanoparticle will come or polycrystalline. So these materials like liposomes comes under three-dimensional nanomaterials. So liposomes are present in our human cells and as well as animal cells. So another example is polycrystalline material, that is also three-dimensional nanomaterial, or and dendrimer. So this is a polymeric nanomaterial. This is recently synthesized. So these are the four types of classified in terms of dimensionality and in terms of shape. These are the shapes of the nanomaterials.
Moving to the next point, now we will see nanomaterial synthesis using high energy ball milling. Let us start.
And how to synthesize. So it is one of the simplest way of making nanoparticle of some metals and alloys in the form of powder. So it is one of the simplest way of making nanoparticles of some metals and alloy. So in the form of powder. So this high energy, it's meant for only metals and alloy. So there are many types of mills such as planetary, vibratory, rod, a tumbler, etc. So these are the mills of the making balls, that is high energy ball millings. So planetary, vibratory, rod and tumbler. So these kind of rotational motions are there to synthesize nanomaterials. Usually, one or more containers are used at a time to make large quantity of fine particles. So for to synthesize this nanomaterial, we have to use one or more number of containers. So that can be used multiple times for to make a large quantity of a fine particle. The size of the container, of course, depend upon the quantity of interest. So how much quantity you want to make, so that much we have to take the size of the container. So it depends on the how much quantity you want to make of the nanoparticle. Fifth point is the hardened steel or tungsten carbide balls are put in containers along with powder or flakes that can be less than 50 micrometer of a material of interest. So hardened steel or tungsten carbide, so these two types of material can be used to synthesize nanomaterials. So this is generally balls. So this is very highest tensile, and this material can crush any kind of material and makes the powder in the powder form of or flakes form. So the size whatever you are putting into the that in ball milling, that size has to be less than 50 micrometer. So that is the one condition. The initial material can be of arbitrary size and shape. So that can be any shape like square, hexagonal, triangular, rectangular, cubes, a trapezoid, any kind of thing. And if you put that kind material shape of material, if you put in the high energy ball milling, and you have to close the container with tight lids, then you have to take 2 is to 1 mass ratio of ball to material is advisable. So your ball suppose is 10 kg and your metal should be like 5 kg. So like that ratio you have to take to obtain a good quality of nanomaterial, a fine quality of nanomaterial. If the container is more than half filled, the efficiency of milling is reduced. So if you filled more than half, your efficiency of the milling will be reduced. Heavy milling balls increase the impact energy on collision, and a larger ball used for milling produce a smaller grain. If you use larger ball, you will get the smaller grains size, but the larger defect in the particles. So this you have to take in proportion only. You cannot take more which is having higher radius of the ball and the smallest grain. If it form also, you will get more defect in the particle. So your particle size will not be uniform. So that is the drawback of the system. So such particle would prefer to acquire a stable lower surface energy state. The container are rotated at high speed, a few hundred of RPM around their own axis. So additionally, they rotate around some central axis and therefore we call it a planetary ball mill. So now we will see the figure of the ball milling, then you can understand better. So this is the schematic diagram of and this is cross sectional of a ball milling vessels. So you will be having a container. So this is half filled, and the you cannot rotate this container with high RPM. So you have to keep it in few hundred RPM around their own axis. So therefore, additionally, they rotate around the some central axis, and therefore call it a planetary ball mill. So that's why we call it a planetary ball mill. So that's why the name is planetary, because it rotates in that way, in planetary way. So by controlling the speed of rotation of the central axis and the container as well as duration of the milling, so it is possible to ground the material to fine powder. So that's how we have to find the material. So you have to control the speed of rotation. So your speed of rotation can be, if you keep how much speed, that type of you will get the nanomaterial size. If you keep higher speed, you will get very fine nanoparticle, and if you keep for longer time also, you will get very fine particle. So that fine powder you will get in terms of few nanometers to few ten, tens of nanometer, so whose size can be quite uniform. So some of the material like cobalt, chromium, tungsten, nickel, tin, aluminum, iron alloy, and gold iron alloy are made nanocrystalline using ball mill. So these are the materials which can be using high energy ball milling. You can make the nanomaterials like cobalt, chromium, tungsten, nickel, tin, like that. So these are the metals. Our procedures are well known to synthesize nanoparticle of these metal atoms. So this is the application of high energy ball milling.
Here we come to end of this lecture. These are the references for the images, and these are the references for books you can follow for this content. So I thank you for your kind listening. See you in next lecture. Till then, happy learning.